Okay, students, this is our last video in this topic of motion and kinematics, and it's an important one because here I'm going to talk about kinematics graphs and motion graphs, and this is something again that every time we study things moving in the next couple of years, we're going to generally refer back to kinematics graphs. They're very useful if you have a deep understanding of them in terms of solving problems, visually interpreting certain kinds of problems, and actually coming up with quantities. So super important here. Now, the simplest kind of graph that we can deal with, dealing with motion, is the graph of position against time or displacement against time. Now, when we do motion graphs, we're always going to have time, almost always going to have time on the x-axis because time is always our independent variable. So in this case, very simple, you have an object that's moving depicted by the red graph here. The relationship between the displacement and the time in this case is a linear one, and you know from before that the slope of a displacement time graph gives you the velocity, okay, or the derivative of a displacement time graph gives you velocity, okay. The velocity, v of t, is actually the slope graph of the displacement graph, s of t, okay. Now, if the displacement time graph is a straight line, then the average velocity is equal to the instantaneous velocity at every single time t. If it's not a straight line, what you need to do to determine the instantaneous velocity is to draw a tangent line at that point and determine the slope, which as we've done before. And still always the average velocity is the total displacement over the total time. So for this particular graph, I have the average velocity being positive 4 meters per second. You need that positive because it tells you that the thing is going forwards, not backwards. And in this case, the average velocity is equal to the instantaneous velocity, as I said, because the graph is linear, okay? Now, in this case, the blue line is a curved displacement time graph, which is a little more interesting and a little more like real life. So here, the instantaneous velocity is not equal to the average velocity because it's not linear. To determine the instantaneous velocity, you have to specify a particular time. So, for example, if I say the instantaneous velocity at 20 seconds, that basically means the slope of that red line right at 20 seconds. And again, there's always going to be a range. With this particular data, I get about 5.2 meters per second. And notice that, again, the average velocity is going to be the slope of the line drawn from the initial point to the final point as a straight line. I get, in this case, it's 3.2 meters per second between 0 seconds and 25 seconds. So really, everything I've depicted to you on this particular slide is pretty much review, okay, at this point. Okay, so again, here's a situation where we have a displacement time graph for a cyclist, okay? In segment 1, he's going quickly forwards as depicted relative to his starting position of 0, okay? In segment 2, he's not doing anything, he's just hanging out between 600 and 1,000 seconds. And then in 3, he's going back to where he started, but more slowly. And you can tell because the magnitude of the slope in this part is less than the magnitude of the slope in segment 1. Note also that he doesn't go back to where he started. He goes back to only a position that's 400 meters from where he started. Okay, so very important that you're able to interpret graphs like this. Okay, so I got that in segment 1, the average velocity is positive 2 meters per second. In segment 2, obviously 0. And in segment 3, I got negative 1 meters per second. Okay, now for the entire trip, the average velocity is plus 0.2 meters per second, which is the slope of that blue line. Notice that this is not the same as the average speed. Okay, the average speed is the total distance over the total time, not the same as the average velocity. That's important to realize. Okay. Okay. Here's another example, which is again more interesting because our displacement axis goes negative. Okay, so in this particular case, the object starts with an initial displacement of negative 10 meters. Now, negative 10 meters, it's relative to some arbitrarily determined 0 point. Okay, so my S naught is my initial displacement is negative 10. My velocity is positive 2 meters per second for t from 0 to 10. Okay, it's negative 2 meters per second from 10 to 15. The object is at the origin right here and right here. Okay, the speeds, it's all 2 meters per second for the entire time. Okay, remember, we're not talking about velocity, we're talking about speed. So the magnitude of the slope of the line in every single, all three segments, 0 to 5, 5 to 10, 10 to 15, is 2 meters per second. Okay, the change in displacement is positive 10 meters because the object ended up 10 meters farther ahead in a positive direction than where it started. It started at negative 10 and it ended up at 0, so that's positive 10 meters. Other things we can compute: the average speed is 2 meters per second because it's the total distance over the total time, which is 30 meters over 15 seconds. That is very different than the average velocity, which ends up being 0.67 meters per second, which is the slope of this blue line. Okay, now velocity time graphs. Slightly more complicated, but it turns out that velocity time graphs are more friendly to you than displacement time graphs because velocity time graphs contain a lot more easily accessible information, and I'll explain what I mean by that. Okay, so again, time is on the x-axis. Here's my velocity here. Okay, the velocity is given by the red straight line here. Notice that v naught, or the initial velocity, is not 0, but this object started off at 5 meters per second at 0 seconds. Okay, now the slope of a velocity time graph gives you acceleration, or in other words, the derivative of v of t gives you a new, it's a slope function, gives you a new function a of t. Okay, so very similar to the relationship between the displacement time graph and the velocity. Okay, now if the velocity time graph is a straight line, as before, the average acceleration equals the instantaneous acceleration. If it's not a straight line, to determine the acceleration, you need to draw a tangent line at that point and determine the slope. Okay, there's one more super important thing that's different about VT graphs, and that is that the area between the velocity time graph and the x-axis equals the displacement, and this area can be positive or negative. Super cool, really cool stuff. Okay, and I'll do tons of examples like this. So in this case, the average acceleration here is the same as the instantaneous acceleration. I got positive 6 meters per second squared when I use that triangle. Okay, again, a more realistic situation is a nonlinear VT graph. Okay, we will usually deal with constant accelerations, which are straight line VT graphs, but you need to be able to understand how to deal with curved graphs. Okay, the distance traveled by this object from 2 to 3 seconds equals the area of this trapezoid, which of course is an approximation because the graph itself is curved. Now, so I get the total displacement here is S1 plus S2, which is approximately 3 meters if you work it out. It should be actually positive. There should be a positive here. It's positive 3 meters. Okay. Now let me just say one word about units. Okay. Do you believe that the acceleration is the gradient of a velocity time graph? Well, if you look at the units, my delta y, my rise over the run, my rise is the change in velocity, which is meters per second, and my run is time, which is seconds. So that's a meter per second, which is a meter per second squared. So that works out. Now, what about the units of displacement? Well, to find this area, for example, S1, what am I doing? I'm multiplying a velocity. Okay, I'm multiplying a change in velocity, which is meters per second. Okay, times a change in time, which is a second. Meters per second times second gives you meters. That's why the units work out, where the area under a VT graph gives you the displacement or the distance traveled in a simpler case. Okay, in this case, I have that the average acceleration is positive 2 meters per second squared. Okay, okay. So just a summary of how these graphs are related. Now, a displacement time graph. An ST graph, the gradient is the velocity. A positive slope means that the object is moving away from the origin. Okay, so for example, in this case, VA equals V sub D. Well, it's not really related to a positive slope, but VA equals V sub D, and in those two cases, the object is actually not moving, but they're at different locations relative to the origin. V sub B in segment B, this object is going positive 2 meters per second, okay? And in V sub C, it's going negative 1 meter per second. In V sub E, this is an approximation because notice that this doesn't actually cross the x-axis right at 9. So I got about negative 1.5 meters per second, okay? A negative slope is an object moving towards the origin or backwards, okay? So in segments B and E, this object is moving back to where it started. Only in segment B is this object moving away from where it started. And just want to point out something. The object ended up further behind where it started by 2 meters. It started at positive 2 meters. After E, it ended up back at 0. So its change in displacement is negative 2 meters. Okay. All right, for the entire trip, I get an average velocity, which is the slope of the blue line, is negative 0.2 meters per second. The average speed, I got 0.67 meters per second, which is the total distance over the total time. Okay? All right, now velocity time graphs. Again, remember I said that these are more friendly to you in terms of providing you more explicit information. Okay, the slope is the acceleration and the area is the displacement. Okay, here's an example of a graph where I have negative velocities and positive velocities. A negative slope, the acceleration is negative. The object is slowing down. Positive slope, the object is speeding up. Okay, in this particular case, the acceleration in segments B, D, and F, it's all 0 because the velocity is not changing. The acceleration in segment A, I got 0.5 meters per second square. In segment C, I got 1 meter per second square. And in segment E, I got negative 1.3 meters per second squared. Okay? And for the entire trip, I get that the average acceleration is negative 0.14 meters per second squared. Okay? Which is, again, the slope of the blue line. Okay, now here's something that you're really going to want to spend some time on in this green box. I have the displacement for different segments, and my magical segment here is, my magical cutoff is about 9.5 seconds. And the reason is because all of this area up here, that's positive displacement. That's going in the positive direction. All of this area over here, between 9.5 and 14 seconds, that's all negative displacements. That's actually, you can think of that as being a negative area and all of this being a positive area. So you have to maintain your positive and negative signs when you're talking about total displacement for segments, okay? So from 0 to 9.5, I got positive 17.5 meters, which is equal to the total area under this entire graph right here above the x-axis. From 9.5 to 14, all of this, the area of all of this is 7.5 meters, but it's negative because it's below the x-axis. From 0 to 14, all you do is you add positive 17.5 and negative 7.5 to get positive 10 meters as the total displacement. Okay, so really important that you understand how areas can be positive and negative. Super important. Let's do a couple of examples. Go ahead and pause the video and try this one. Okay, a mass starts out from O with a velocity of 10 meters per second as depicted, continues for 5 seconds, the velocity is reversed to negative 5 meters per second, and the object moves at this velocity for 10 seconds. You should spend some time thinking about what this object would look like. Okay, remember the motion graphs activity that we did, okay, where we tried to match the graphs? This is kind of like that, okay? So you're moving away from the origin pretty quickly, and then all of a sudden you move towards it half as fast, if you can imagine that, okay? So the total change in, or the change in displacement is 0 meters, okay? Because it turns out that the displacement, okay, this area right here is the same magnitude as this area, but this area is negative and this area is positive, so you get 0 meters, okay? But the total distance is very different. That's 100 meters, okay, because of 50 plus 50. The average speed, okay, there are 3 segments. I got an average speed of 6.7 meters per second and an average velocity of 0 meters per second because the total, change in displacement was 0, okay? Okay. Acceleration time graphs, you see these once in a while. A couple of things that are really important to know. The area between an acceleration time graph and the x-axis is the actual velocity. The slope, the slope of an AT graph is actually called a jerk, which is kind of one of the funniest units in physics. How we measure jerk, we use a jerk meter. Anyway, I'm not going to get into that, but it's kind of funny. That's not really part of the IB syllabus, but I thought you would be interested in that. You should be able to take an AT graph and work backwards to find a VT and an ST graph. Additionally, be able to work forwards from an ST graph to an AT graph, and we will, we'll do examples of that in class of what I mean by that. Okay. Okay. So, for example, 13, what you want to do, pause the video and sketch these graphs. Okay, so I give you a VT graph, and I want you to sketch a displacement time and an acceleration time graph corresponding to this particular VT graph, okay? It turns out that the acceleration graph is a straight horizontal line because the slope of the VT graph is negative and constant, okay? Now, it turns out that the displacement time graph is a concave down quadratic curve here, all right? If you don't believe it, what you want to do is you want to draw some tangent lines to this curve, and you see that if you graph the slope function of this ST graph, you end up with a straight line VT graph. Very interesting. Again, we'll do more practice on that in class. I'm going to bring calculus back into your life here for a second, okay? The way the graphs are related, if I have a displacement time graph given by the blue graph right here, okay? The slope graph of that is depicted by the red function down here, and you should pause the video and think very carefully about how this slope function matches that blue function right there, okay? Everywhere on this side the slope should be positive, and it is right here. Everywhere on this side the slope should be negative, and it is over here. There's only one point where the slope is 0, and that it's at the very, very, very top of that curve, and that's depicted right here in this graph, okay? So we say that the derivative of s of t gives you v of t. A couple of different ways to write this. We can write it ds by dt, or s prime of t is how you guys are going to write the derivative when you guys study that in mathematics, okay? So the slope graph is the derivative of the st graph. Now, a very, very close analogy here. It turns out that the derivative of a VT graph gives you a of t, okay? So dv by dt is v prime of t, which equals a of t. This is actually this exact same mathematical function, but now if this is v of t, the slope function of that, or the derivative of that graph, gives this graph down here, okay? Again, positive over here, negative over here, and just right there, there's only one point where it's 0, and that's right there in the middle, okay? Now, it turns out that the ST, the displacement time graph, is an area graph. That is actually the integral of the velocity time graph. Remember how I said that the displacement is equal to the area between the velocity time graph and the x-axis? Turns out we take what's called an antiderivative or an integral, and the way we write it, again, you don't need to know this right now, but it's just kind of interesting. The way we write it is the integral, which is this kind of snaky looking integrand, it's called an integrand, of v of t times dt equals s of t, okay? And it's also true that the integral of the acceleration gives you the velocity, okay? But we're not really going to talk about that at this point. Don't worry about the calculus, just worry about really the derivatives and how to interpret graphs in terms of slope graphs.